we have seen the dysentery algorithm is very good algorithm in the sense that it gives good explainabilities, and we can create the tree, but that has some limitations. We'll see that how we can use dysentery for making in the random forest algorithm. But before going to talk about random forest algorithm, we have to understand what is ensemble methods, because random forest algorithm is again a kind of ensemble technique. Okay, so the idea of ensemble method is that we generally construct base classifiers learned from the training data, and we make a lot of base classifiers basically. So we create a set of base classifiers, and then we try to predict the class label based on the predictions made by all of the base classifiers, and we take the majority voting. So this is a general definition that in ensemble models, we try to make multiple models, small models, base models, or weak classifiers. And then from all those models, we try to combine the predictions. And then we see that how that kind of situation and that kind of ensembling technique improves the results over the individual classifiers. Okay, so that is a broad idea, and then we'll talk about how we can do in ensemble techniques. Okay, so in when we try to develop an ensemble model, you can see this diagram in which we have a training data D, and the first step is that we create multiple classifiers. So for this example, we have C1, C2, CT classifiers. And from these T classifiers, the next step is that we combine the results. So for example, if it is a classification problem, we can combine the predictions of each classifier by taking the majority voting. We can also assign weighted majority voting depending upon the giving importance to a particular classifier and so on. And if it is a regression problem, if you want to use it the regression, so we can also do the averaging of the predictions of each of the classifiers. But the most important concept in ensemble learning is that complementary models. So the complementary model is the most important concept that we have to understand before going to into detail of the any kind of ensemble techniques. So the in complementary model means that the training data which we have, and from that we when we try to create multiple models or multiple classifiers, the one and only the most important attribute or the characteristic which we would like to see is that all these models should be complementary to each other. If we will not have these complementary models, then we may not get the improvement of the overall performance of the ensemble technique. We'll understand why it is important and why mathematically that if you have complementary models, in that case, we'll have most probably will get the improvement. Complementary model means that if we talk about C1, so after the training, if we train this model, so the performance of the C1 is not depending upon C2, and C2 is doing learning different characteristics of the training data. C1 is doing and learning different characteristics of the data. And similarly for all the models are basically learning different kind of pattern, different kind of characteristics. It is just like if we have a group of people, if a team is doing some work, if we are in a complementary skills, so that project and that team will always do better as compared to the work individually. So same idea here is that the models which we have should be complementary to each other. So in all the ensemble techniques here and there, what we try to do is we try to force these models to be complementary to each other. And for that, we have different ways, we have different techniques that we use for creating these kind of these multiple models to be complementary. Okay, so that is the most important concept that we have to keep in mind. Now let's understand why assembling technique will work with this example that let's say we appease the probability that a single classifier makes a wrong prediction, and let's say n is the total number of classifiers. Generally we take odd number of classifiers because of avoiding ties during the majority voting. And ensemble model, if we'll take n classifiers, so in that case the ensemble model will make a wrong prediction if more than half of the classifiers are wrong. So ensemble model will make wrong decision only when we have more than n half of n by 2 classifiers are incorrect. And that way we can compute using the binomial distribution that what is the probability that ensemble model will do wrong prediction is this. And suppose we have 25, for the example, 25 base classifiers, and suppose each classifier is having an error rate of 0.35, and assuming that all the classifiers are independent, it means complementary to each other, and the probability in that example is that the classifier ensemble classifier make a wrong prediction is very small, 0.06. So mathematically, if we are able to make a combination of the model which are complementary to each other, independent to each other, they are learning different patterns, different characteristics in the training data, will most probably get improvement in the overall results. So that is why ensemble technique will not always work, but it should work if the conditions we follow. Okay. And in one of the research also, it is shown that ensemble method work better than a classifier if all base classifier are independent of each other, and all base classifiers perform better than the random guessing. That is error rate is less than 0.5 for the binary classification. So if you'll notice on this graph that if we have base classifier errors less than 0.5, so it means better than the random guessing. And in that case, if we combine, then the ensemble classifier is always doing a better performance. So if you'll notice that by having the individual classifiers base classifier error is even if 0.3, so we are getting very low ensemble classifier error. Okay, so that has been seen with the empirical results with the different classifiers. And the only thing is we have to ensure that the models which we are using for ensembling purpose are independent and complementary to each other. Okay, so that is important thing. And now next is we have to decide that how we can find out the models which are complementary. So in that case, in ensemble learning, we try to use unstable base classifiers. Okay, so it works best with unstable base classifiers, and the classifiers that are sensitive to minor perturbation in the training set due to high model complexity, for example, unpruned decision tree, artificial neural network, KNN, these with ensembling models with these algorithms works good. So the stable models are like support vector machine, and also they are not very prone to minor changes in the training data. And that is a very good requirement for the ensemble method, because what we want to do in ensemble model is that all the models or the classifiers, weak classifiers, should be complementary to each other. And if the model is unstable, they will have different models or different characteristics. So unstable classifier is a model that is highly sensitive to small changes in the training data. Even a slight variation can lead to a very different model of the prediction. And that is the reason that ensemble learning is basically work good for these kind of algorithms. Okay. And one more thing is that unstable classifier exhibits high variance, meaning its predictions can vary significantly depending upon the particular sample of the training data. So it means that the unstable classifier will be highly variable. And that case, the model which ensemble model which will use this kind of base classifier will generally have complementary models. Yeah. So ensemble models, as we have discussed, there are two kinds of ensemble methods. One is bagging, which we'll talk about in this session, and another is boosting. So there are two ways to combine different models. One is bagging and another is boosting. In bagging, we'll talk in this session in which we have multiple classifiers and we combine the results, and all the models which we use for the ensembling are treated equally. But in boosting, all those weak classifiers, they are basically used in a particular sequence based on how first classifier is doing misclassification. So in boosting, generally we give high weights to the wrong predictions made by the first classifier and so on to the last classifier. But we'll talk in this session, we'll just talk about the bagging and the random forest. Random forest is one way of doing the assembly technique based on the bagging technique. Okay. So in bagging, they rely mostly on diversity among the base learners. Unstable classifiers, which we have talked when we train on different bootstrap samples. What we'll talk about bootstrap, what is the bootstrapping or weighted data sets, and that in subsequent slides. But at this moment, what we try to do is we are in bagging and random forest, we are basically relying on the diversity among the base classifiers, and all these classifiers are taken equally, and then the output of each of these base classifiers are taken as a majority voting or the averaging depending upon the problem. Okay, so that is the way we will be doing in the bag. And in bagging, as you already know that what is bias and variance, underfitting and overfitting, but just to make this talk complete, I just want to take 2 minutes to just repeat the things which you already have discussed, that a model is best when you have, based on the complexity. If it is very less in the complexity, it means you will have very high bias, and it means the model is underfit. And when you increase the complexity of the model, your variance becomes high, and the model becomes overfit. So the problem which we seen in the decision tree also, that the model, if we increase the model complexity, we face the problem of overfitting. And ensemble technique try to tackle this kind of problem, that is overfitting problem, and it will try to deal with this overfitting problem of the decision trees and other algorithms also by by reducing the complexity of the individual classifiers and by averaging the results of the of all those big classifiers. Okay, so model is underfit means there is a high bias and low variance, and the model, if it is complex, then your model is basically overfitting and there is low bias. Okay, so ensemble techniques, particularly random forest and bagging, will try to deal with this problem of overfitting and high variance. So in ensemble classifier, the objective is to make the models complementary to each other. And for that, given the training samples, what we do is we try to make manipulations in the training set. It means how we take original data set and change in the training data to make the classifiers C1, C2, and so on in a way that all these classifiers learn different characteristics. So we'll see that how we can make the manipulations, or we'll see differently will give the different data from the original training sets to each of the classifier, just to make classifiers complementary. And one another way is that we'll see in the random forest, that we also see manipulate the input features. Okay, so the key idea here is that when we'll try to make ensemble classifiers from a given training data, we either do changes or do different sub training data to each of the classifier, and we can also go for taking subset of the features for training of the models. Okay, so in bagging generally we do manipulation of the training sets, but in general in random forest we also do the manipulations in the input features. So let's first understand, since the random forest is a kind of a bagging technique, and in bagging technique, which is called as a bootstrap aggregating. Bootstrap aggregating means in bagging we focus on, we do the classification in two major steps. One is the bootstrap and second is aggregating. First is the bootstrap. It means that from the original training sets, we'll try to make multiple data sets, D1, D2, and so on, and we'll try to make these data sets in a way that when we use C1, C2, C3, and so on, in a way that it will learn different kinds of training data. So somehow they will be forced to learn complementary skills or complementary characteristics of the training data. And that is one way of doing the manipulations in the original training data. And second step is the aggregation. Aggregation is very simple, that we do the like combination of the results, combining the results of each of the classifiers. So if it is a classification problem, we do the majority voting, and if we have a regression problem, we can do the averaging of the predictions of each of the classifiers. Okay, so now we'll understand what is the way that we'll do the bootstrap process for creating these subset of the data, and then we'll understand how aggregation can be used. So this is one of the most important idea in bagging, and this is bootstrap process, in which uh, what we do is, from this original data, for this example, we have 3 samples, and in first, this is D1, in which if we try to get to D1, so what we will do is we'll randomly select the samples with replacement from the original data. So what we'll be doing is from let's say from these 3 samples, first is we'll select some samples there with replacement techniques. In that case, there will be duplications of the data. Okay, so we do the we select n number of samples. So for this example, 3 samples are there in the original data. We'll do the random selection with replacement technique, but in that case we may have duplicate data. So originally, so the data set D1 will be somehow less number as compared to the original data, and we do it for n number of times, D1, D2, and so on, the number of classifiers which we want to create. So again, this is an hyperparameter that we have to decide that how many V classifiers you like to have in the ensemble technique. Okay, so now we'll try to see that why this kind of technique will help us in creating complementary models. Okay, so from this diagram you can also visualize that if we have 3 samples, 1, 2, and 3, and from first data set D1, it is not having sample 2, and in the second it is having all the samples, but in D3, so the last sample, it is having it is not having third sample. So the classifier made from D1 will, let's say, C1, and the classifier made from this may have a different attributes, different characteristics that will be learned in C2 and C1. Okay, so this is the way that giving different training data with the same distribution of the original data, but with the different samples, it is likely that the model which we train may have different learning the characteristics that is learned from the training data. Okay, so that is one way of making complementary classifiers. So each bootstrap sample is created by randomly sampling n times with replacement for a data set with n instances that we have just seen. And one of the important thing here is on an average, it is seen that on an average, each bootstrap sample will have 63% of the instances and will you can see that when we do with replacement, we can get less number of samples. And because of this, the models which will be learned from the 63% of the original data will have, the classifier will have uncorrelated errors because they have learned from different data. And that is why this technique somehow works. Okay. And in bagging, we generally do averaging because in the average, when we do the averaging from multiple classifiers, it will reduce the variance because of the averaging. And if you have bootstrapping process, so plenty of training data if we have, so that we can create multiple subset of the data, and by averaging it will reduce the variance, high variance, which might be prevalent in the individual classifier. Okay. So the process of creating a bagging model is we generally firstly create n bootstrap data sets using the method which we just see, randomly sampling with replacement from the original data. And then we train n models, that the learning algorithm which we want to learn for each of the data. And then we make the predictions from each of these models, so that we already discussed it. Now, this is called out of bag error because we have seen that when we do the bootstrapping process, in bootstrapping process, in general, 2/3 of the observations are basically picked up, and remaining 1/3 of the observations may be used for the testing. Because when we do the subsampling, so for each of the subsample, remaining 1/3 of the observations we can use for the testing, and that is called as out of bag error estimation. And that can be used for further improvement of that particular model, and that can also be used for estimation of the error. And one more thing about the bagging process is that in bagging, generally the prediction accuracy is increased by aggregating the results of many models, but it also sacrifices the interpretability and the explainability, which we have seen that in the decision tree, we can visualize that what is the reason of that the particular outcome based on the rules, which rule is giving, which by because of which rule and which feature the particular outcome is the which we have seen. Okay, so in bagging and in the ensemble technique, we basically lose the interpretability and explainability, because when we have multiple classifiers, it is very difficult to know that what is the reason that a particular outcome has been arrived. Okay, so that is mostly a process of doing the bagging process for creating an ensemble model. And to summarize here, the the bagging, in the bagging process, we firstly do the bootstrap process. In the bootstrap process for the bagging, we take a subset of the samples, training samples, and give different subsets of the training data to different classifiers. And we assume that all the classifiers, because of having different the different training data, will learn different characteristics of the data. And then with the help of aggregation, because we are averaging the results of many classifiers, so variations will be average out, and so variance problem, the high variance problem of individual classifier somehow reduces. because when we average, so because as you've seen that more than half of the classifier should be, give the wrong predictions if there is a wrong prediction. So when we do the averaging, so by doing the averaging, it will reduce the variations in the outcome of the classifiers. So that is why ensembling technique sometimes gives better results. The only thing is we have complementary models, and we use different techniques to develop complementary models. In bagging, it is not necessary that we use a particular only one model, but we can also use different models in each of the classifiers. We can have same classifier or same algorithm for each classifier, and we can have different classifiers, but it depends. But in random forest, we'll see that in random forest, we'll use the idea of bagging, and in the classifier, particularly for all the C1, C2, and all these classifier, will only use decision tree, and that is random forest. So this is also called as a decision forest. So this is basically bagging of decision trees. So random forest algorithm basically use a decision tree as a weak classifier or the base classifiers when we are doing the ensembling process. Okay. So about decision tree, we have seen that it is very easy to achieve 0% error on training data, because we have seen that for each training example, it can have its own leaf, and it can have its own that rule from the data. So if there is a noise, so even that it can have that particular rule for that particular sample, and that way we can have 0% error on the training data, and that can be solved with the random forest algorithm. In the random forest algorithm, bagging of decision tree, in which resampling of the training data is not sufficient. Why it is not sufficient? Because when we do the bagging and the bootstrap process, which we have seen, is like okay, man, let me go to that. So when we do this kind of D1, D2, D3, and so on, and we try to make a classify C1 or decision tree. So if we'll have D1, in that case, if we'll try to make C1. So if you remember decision tree, in that case, firstly, we try to find out the best attribute. So if we have a best attribute, which is having highest information gain, and okay, so in that case, if we have बाद में आधे घंटे बाद में, हाँ बाद में आधे घंटे. So in that case, if a particular attribute is there, okay, so in all the classifiers, even if we take sub samples or less number of samples, even if that is the situation, but when we are having all the features, it is likely that the feature which is important for D1 will also be important for D2. So for example, age is a attribute which is available in D1 and age is also available in D2. It is likely that we may have similar kind of trees. So the method which we do in bagging for the bootstrapping of the creating different subsets of the data may not work as it is in random forest. And that is why we do subsampling in the features as well. And that is the reason that we do manipulations in the features itself. Okay. So resampling of the training data is not sufficient, because even if we do the resampling of the training data, it is possible if a particular feature is having same distribution, even if same distribution, in that case, if we do if we'll try to find out the information gain, that particular feature is still maybe most important, and that way it is possible that the trees which we create in create for from different subsets that is having same trees. And that is why we randomly restrict the features for the split. So what we'll do is in bootstrap process for random forest, we'll also subselect or resample the features. So build a number of decision trees on bootstrap training samples, but when building these trees, each time a split in a tree is considered, a random sample of M predictors is chosen as a split candidate from the full set of P predictors. So if we have total P attributes, in that case, we'll randomly select M attributes when we'll be doing bootstrap process. Or in general, M is equals to root of P. So total number of attributes will take the square root, and we generally take that number of samples only. Okay, so that is the very important and the important difference between bagging and random forest, that in random forest in, we also do the resampling the training samples and resampling the features as well. And the reason of doing the resampling the feature set is that we try to force the C1, C2, all the classifiers to be complementary and to make trees which is different from different in all the classifiers, and that we can force only with taking the subsampling in the feature set. Okay, so if we this is, we already discussed that if the data set contains one very strong predictor along with several moderately strong ones, most bacteria will likely use the strong predictor or the attribute for the first split, and that may create the trees which are very similar. As a result, their predictions become highly correlated, and averaging them offers limited variation reduction, and that basically not desirable in our ensembling method. And to address this, random forest introduces randomness to decorrelate the trees, achieving greater variance reduction, and improve performance by some sampling in the features. Okay, so two sources of randomness which we have seen in random forest, we do subsampling at training set and also at the feature set. And in bagging, tree is grown using bootstrap samples of the training data, and random vector method means we also do the subset selection and subset selections from all the given attributes. Okay, so this is kind of way of introducing the randomness or the variation in the input data that we give to each of the classifier and force each of the classifier to learn different characteristics of the training data. Okay, so now we'll understand this more thoroughly. That random forest algorithm. In random forest algorithm is basically a collection of decision trees. In each of these decision tree, we give each of the decision tree will give a vote, and which is basically an outcome of this particular tree, and we then do the majority voting for each of the predictions of the trees, and then we combine the results. So this is very similar to what we have seen in the bagging process, but the two major differences here is that the way that we create D1, D2, and so on. And second is the classifier which we are using here is our decision trees. So, sorry, just a second. I'm sorry for the disturbance. Uh, so So basically there are two major differences which we have discussed in random forest and bagging. And the most important thing here is that how we create multiple data sets, bootstrap process. And second is that for each of the V classifier we are using decision tree. Okay, so and you can observe that if we'll give different attributes to each of the classifier, the tree will always be different. So because we are in each of the data set, no two features are common. So we are giving different features in each of the classifier. So they will take different features as a root element, and then it will be different and complementary results. So in bagging and random forest, we have already seen the difference that it is the random forest introduces the randomness into the rows and columns, but in bagging we only introduce the randomness in the case of the rows. And combining this diverse set of trees, we always get lower predictions error because of the averaging. Okay, so that is important concept for the base classifier, that it will always work with good with the if the base classifiers are unstable and complement to each other. And it will increase the accuracy because it reduces the variance of the individual classifier by averaging. And it does not focus on any particular instance of the training data, and therefore it is less susceptible to the model of overfitting when applied to noisy data. So that is why the random forest and the bagging ensemble techniques will always work very good if we have that complementary models. And it is also seen in the literature that we can measure that classifiers are complementary or not, and we can find out that which are the models which are complementary, and taking the complementary models and then doing the combination, we always get the improvement in the overall performance. Okay, so that is it for random forest and bagging algorithm. The key idea here is that whenever we do the ensembling technique, we always focus on forcing the models to be complementary, and we generally have all these kind of models to be equally weighted, and we can also give weights to each of the classifiers also. But in boosting way of assembly technique, in which we have basically sequence all the classifiers in a way that first classifier, if it is giving misclassifications to particular samples, we give the more weights to those samples, and then we do that iteratively. So somehow in all the assembly technique, we try to make the models which are complementary and expert in a particular thing. In boosting also, we try to find out the model which is doing good for particular samples, to give more weights to that particular samples which are misclassified to the another class, and so on. So the idea of making the models complementary and then see how we can force the model to do in that sense is the key idea of making the ensembling techniques. Okay, so thank you very much, and please let me know if you have any questions on this topic. Please feel free to ask questions in the chat.